So, hello everyone, how are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. I'm Aman, just welcoming you all to a new amazing video in which we are gonna talk about a really crazy thing in this video. Like, this is really crazy. You know what? It's not for us, and I was just wondering about this, and literally, I just got something that look. Basically, the thing that we are going to do in this video today is being used somewhere in the proof of a crazy thing, like a beastie thing. Let me just write that down for you guys. Okay, so basically, it is. Let me just write that down. So it's 1 over pi equals 2 root 2 over 9801 times this sum as k goes from 0 to infinity of 4k factorial and times it's 1103 plus 1103 plus 23 I think 960 oh 26390 I'm sorry 26 it's 390 k right over it's k factorial to the fourth and 396 to the 4k. And now you would ask me, what have you written there? What is this? So I would say this is the Ramanujan's approximation of pi. Of pi. Wow. You know what? This is a perfect example which shows Ramanujan's deep, like literally so deep interest in infinite series. Like literally, he just computed an infinite sum which is literally mind blowing, or maybe I would say it is nested a lot of things in it, and that gives 1 over pi. Whoa, that's really crazy and it is really amazing. And well, you know what? I was just wondering about the proof of this thing, because we need to care about the proof, because on my channel, if you are learning something, so you need to just get something that proves the thing that we are learning, right? And I really care about that. But we are not gonna we're not gonna tackle this in this video, because this is not in my zone. I would be frank, right? I would be honest, and I cannot prove this down by the knowledge of mine till now. But I can make sure that if I would have enough amount of knowledge about the things that can help us to prove this down, I will absolutely bring a video. And like, that video is gonna be literally mind-blowing and crazy. So basically, we are going to talk about in this video in something elliptic integrals. And you know what? Elliptic integral play a crucial role in the proof of this thing, right? So that is why maybe you can understand this as the base which will help us in future to prove this down. So that is why I'm here to just make a foundation of that. So basically, elliptic integral is k of a is the integral from 0 to pi over 2 of d theta over its square root of 1 minus k squared sine squared theta. And you know what? Basically, we are gonna take a look at this thing. We have to just calculate the closed form of k of 1 over square root of 2, which means on the place of small k in this integral, like here, we have to replace it with 1 over square root 2, and let's just find the value of that. It's not easy and it's not simple at all. We will be needing a lot of things, and basically I would say the beta function, right? So please, if you haven't watched my beta function video so you have to watch that firstly, because we are going to use that video a lot in this video. So yeah, okay, now let's just come back to the proof. So our journey begins with the beta function's definition. That is, beta of m comma n was, as we have studied so far, it was the integral from 0 to 1 of t to the m minus 1 times 1 minus t to the n minus 1 dt. And you know what? I have proved that this evaluated to gamma of m times gamma of n over gamma of m plus n. Right? And another prerequisite for this video, even I have proved this down as well. The gamma of 1 over 2 is the square root of pi. Well, you can just prove this down using the Euler's reflection formula. I have did a lot of times, so I'm not going to just repeat that here once more. Okay, now let's talk about the beta function at some same value, which is beta of a comma a. So it's integral from 0 to 1 of t to the a minus 1 and 1 minus t to the a minus 1 and dt. Okay. Now let's just use some use substitutions. That is, I would say that t equals 1 minus u over 2. So if we talk about 1 minus t, so that's gonna give us 1 plus u over 2. Well, you can check that out. And if we talk about the limits, so when t is 0, so it's u is 1, and when t is 1, so u is gonna be negative 1, right? Okay, and now if we talk about the derivative, so here we would say dt equals negative du over 2. Wow. Now let's just plug all the things back in our beta of a comma a, which is beta of a comma a equals the integral from 1 to minus 1 actually, right? And we are having t equals 1 minus u over 2 to the a minus 1, and it's 1 plus u to the over 2 to the a minus 1, and we are having d u over 2. So this negative sign is going to help us to just change the bounds in between them, because it's not a proper integral, right? So basically it is beta of a comma a equals the integral from negative 1 to 1 of, we can say it's 1 minus u to the a minus 1 over 2 to the a minus 1 times 1 plus u to the a minus 1 over 2 to the a minus 1, and we're having du over 2. We can just combine these three things with each other, so we would be ending up with 2 to the 2a minus 1, right? And if we combine the numerator as well, so we would be having 1 minus u squared over to the a minus 1. So basically it is 1 over 2 to the 2a minus 1, because it's a constant, and it's negative 1 to the 1. Negative 1 to 1. It's 1 minus u squared to the a minus 1 du. And now since u squared is an even function, so we can just we can consider writing this integral 2 times, and the integral from 0 to 1. So yeah, or maybe we can just divide this 2 in between here, so that's gonna give us a negative 2 here. I hope you are familiar with all these things that we have did so far. Okay. Now, so basically we are having beta of a comma a equals 1 over 2 to the 2a minus 2 actually, sorry, and times integral from 0 to 1 of u1 minus u square to the a minus 1 du. Wait a second, let me just check. I think everything is, yeah. Okay, now our next step is let u squared equals s. So from here we can say that u equals the square root of s, and it's 2u du equals ds. So du equals ds over 2 square root of s. And if we talk about the limits, so limits ain't gonna change, right? So basically we will be ending up with beta of a comma a equals it's 1 over 2 to the 2a minus 2 and times to this factor and integral from 0 to 1, and it's 1 minus s actually because u square was s, and we have ds over the square root of s, right? And well, if we talk about this integral, so we can write this as integral from 0 to 1 of s to the 1 over 2 minus 1, because s to the 1 over 2 minus 1 is s to the negative 1 over 2, right? And that would be ending up with 1 over square root of s. So I have written this square root of s in terms of something like that. And we have 1 minus s to the a minus 1. And from the definition of beta function, so we are having n equals 1 over 2 here, right? And n equals a. So this is coming out to be beta of 1 over 2 comma a. Isn't that crazy, guys? Like, let me just write that down on the board. Like basically we are having beta of a comma a equals, it came out to be beta of a comma a equals 1 over, well, this 2, if we multiply that, so we would be ending up with a negative 1 here rather than negative 2. So it's 2 to the 2a minus 1 and times beta of 1 over 2 times a. I'm sorry, 1 over 2 comma a. Wow, like that's a pretty good result. Maybe we can use this in some sort of a beta function questions if we need it. Now let's just talk about this beta function actually. So beta of 1 over 2 comma a. So from the result we can say it's gamma of 1 over 2 times gamma of a over gamma of a plus 1 over 2. Like I have proven this, I have proved this down, and if you want I can just paste the link of that video in the description box of this video. And as I told you to just remember that gamma of 1 over 2 was the square root of pi. So let's just plug that over there. So basically we will be ending up here beta of 1 over 2 comma a is the square root of pi times gamma of a over gamma of e plus 1 over 2. Right? And now let's just plug it back into our equation, right? Okay. Now you would ask me, Aman, we are literally not using the elliptic integral which we need for the proof of the Ramanujan's pi formula. So I would say just be patient for some time. I'll get back to that soon, don't worry. So it is beta of a comma a equals, this can be written as the square root of pi over 2 to the 2a minus 1, right, minus 1, and we have gamma of a over gamma of a plus 1 over 2. Now set a equals 1 over 4 here. So it is beta of 1 over 4 comma 1 over 4. It is the square root of pi 2 to the 2 times 1 over 4 minus 1, and it's gamma of 1 over 4 over gamma of 1 over 4 plus, well, I can write this 1 over 2 as 2 over 4. So basically, beta of 1 over 4 comma 1 over 4 comes out to be, this is a 2 over 4, which is 1 over 2, and 1 over 2 minus 1, it's negative 1 over 2. So it is the square root of pi over 2 to the negative 1 over 2, right? And it's gamma of 1 over 4, and if we combine this, so it's gamma of 3 over 4. Now we are going to use a crazy result that already we have proven a lot of times. So that is the Euler's reflection formula. So we know about the Euler's reflection formula, that is Euler's reflection formula. So it is gamma of z times gamma of 1 minus z equals pi over sine pi z. Right. Okay. Now for our case, we have to look for 3 over 4. So let's just plug z equals 1 over 4 here. So it's gamma of 1 over 4, gamma of 1 minus 1 over 4. Well, well, 1 can be written as 4 over 4. So that's going to give us 3 over 4. So let me just write that down. So it's 3 over 4 equals pi over sine pi over 4. Right? Okay, sine pi over 4 is 1 over the square root of 2, right? So from here we can say gamma of 1 over 4 times gamma of 3 over 4 equals pi over 1 over the square root of 2. And that can also be written as pi the square root of 2. So basically from here we can say gamma of 3 over 4 equals pi the square root of 2 over gamma of 1 over 4. So, so we have used the Euler's reflection formula to calculate the gamma of 3 over 4, and now we are gonna plug this result here, right? And yeah, let's just do that. And I think that's our last step for this first part. And then we will move to the elliptic integral. Okay, so from there we're having beta of 1 over 4 comma 1 over 4 equals square root of 2 square root of pi. Well, this can also be written as this can be like written as the square root of 2 in the numerator, right? So we can combine them and we would say it's the square root of 2 pi. I hope that's the basic exponential rule, so you can understand that. And it's gamma of 1 over 4, and gamma of 3 over 4 can be written as pi root 2 over gamma of 1 over 4. So this root 2 and this square root of 2 cancels out, and this square root of pi would cancel out with the square root of pi, and we would be left with the square root of pi in the denominator. So basically it's beta of 1 over 4 comma 1 over 4 comes out to be gamma times gamma squared of 1 over 4 over square root of pi. Finally, so we did our first step here. So let me just write that down. Beta of 1 over 4 comma 1 over 4 evaluated to gamma squared of 1 over 4 and over the square root of pi. Now we are gonna look for the elliptic integral, and basically that is evaluated at k small k equals the square root of pi. I'm sorry, 1 over square root of 2 actually. Wait a second. Okay. So as I have talked about the elliptic integral, so basically elliptic integral is k of k integral from 0 to pi over 2 of d theta over the square root 1 minus k squared sine squared theta. So for k of 1 over square root of 2, it is the integral from 0 to pi over 2 of d theta over the square root of 1 minus 1 over square root of whole squared sine squared theta. And finally, we can say that it is the k of 1 over square root of 2 actually. It's the integral from 0 to pi over 2 of d theta over the square root of wait a second guys, let me just check the recording is happening. Yeah, it's fine. Actually, I think my hotspot was turned on, so my phone got heat up. I think I just got saying that. So it is a sine squared theta over 2. Wow, that's good. Now let's just consider, let t equals sine squared theta. So if you talk about the limits, so 0 is gonna be 0 and pi over 2 is gonna be 1, right? So basically our k of, wait a second, k of 1 over square root of 2 is integral from 0 to 1, and if we talk about the derivative of dt, the derivative factor, it's 2 sine theta cos theta d theta, right? So basically d theta equals 2, dt over, if we write sine theta and cosine theta in terms of t, so that would be 2 times the square root of t and times the square root of 1 minus t, because our t was sine square theta. So for cosine theta, it is the square root of 1 minus t, which is 1 minus the square root of 1 minus the sine square theta. So yeah, I hope you just understand that, right? Okay, so now let's just plug all of them back inside our integral. So it's 1 over the square root of 1 minus, it was t over 2, and we had dt over 2 times the square root of 2 and times the square root of 1 minus 2 as well. So our k of evaluated at 1 over square root of 2 equals 1 over 2 integral from 0 to 1, and it's dt over, we can just combine all these three terms because they are in a square root form, so we can just multiply them inside and in square root, a common square root, I think. So we can write this as 2 minus t over 2, and it's t and 1 minus t, right? Okay, now this can be factored out because it's it could be factored out with this 1 over square root of 2. So basically we can say it's k of 1 over square root of 2 equals, this square root of 2 would be in front in the numerator actually, so it's the square root of 2 over 2, and integral from 0 to 1 of dt over the square root of it's t times, or maybe I think right, 2 minus t and 1 minus t. Wow, fine. Yeah, I should extend this a little bit. Yeah, now it's good. And now we are gonna assume something here. 1 minus t equals, let's say, u. 1 minus t equals u. So our next our u sub is gonna be t equals 1 minus s, right? So basically t equals 1 minus s. So yeah, let's just, so our next u sub here for that integral is t equals 1 minus s. So 2 minus t is 2 minus 1 plus s, which is 1 plus s. And if we talk about 1 minus t, so it's 1 minus t, 1 minus 1 plus s, so it's s. So these things we are having so far, s, 1 plus s, and 1 minus s, right? And if we talk about the derivative factor, so dt equals minus ds. And if we talk about the limits, so when you plug t equals 0, s comes out to be 1, and if you plug t equals 1, s comes out to be 0. So basically this negative factor or the derivative negative the differentiating factor is going to help us to change the limits as well for this integral. So finally we would be having k of 1 over root 2 integral from 0 to 1 of I would say it's ds over its square root of this was 1 plus s and 1 minus s. Yeah, now it's good. Sounds good, right? Now we can combine this 1 plus s with this 1 minus s. So k of 1 over root 2 equals integral from 0 to 1. Oh, I think I just forgot the factor that is the square root of 2 over 2. Oh gosh. Okay, now I just remember that. Don't worry. Okay, so now it's ds over it's s times 1 minus s squared. Okay, and now it sounds good. Now another use up here. So let's s squared equals u. So 2s ds equals du, right? So and if we talk about I think s equals u squared. We have to assume here. Or wait a second. Wait a second, guys. I think u squared equals s. Oh. Wait a second. Oh, I'm sorry, guys. Okay. So we have to assume that u squared equals s. So 2u du is gonna be ds, and limits are gonna be same. So our k of 1 over root 2 equals the square root of 2 over 2 times integral from 0 to 1, and it's 2u du over s equals u squared. It means that it is u, so it's u and times the square root of 1 minus this s squared equals u to the 4. So we just got rid of this u and as well as this factor. Wow, now that sounds good. Oh, did I miss something there? Oh, yeah. So, yeah, fine. That's good. Actually, it's a kind of long thing. That is why I have to just clear each and every step. So, yeah. Now let's just move on further. So, we are here with k of 1 over square root of 2 equals the square root of 2 and times integral from 0 to 1 of du over the square root of 1 minus u to the 4th. Now next what? Now next we are gonna consider, now we are gonna consider u to the 4th. This is 4th, right? So u to the 4th equals v, a final use of I think. And from here we can say u equals v to the 1 over 4. So du is gonna be 1 over 4 v to the negative 3 over 4 dv. Oh my god. So yeah, it's k of 1 over the square root of 2 equals the square root of 2 and this factor 1 over 4 and integral. If we talk about the limits, so again limits ain't gonna bother us, and it is v to the negative 3 over 4 dv over its square root of 1 minus v, right? Okay, now let's just do something there, and believe me guys, you are gonna have a goosebump there, guaranteed. Okay, so k of 1 over the square root of 2 equals the square root of 2 over 4 and times integral from 0 to 1. Well, we can write this as v to the negative 3 over 4. We can write this as v to the 1 minus 3 over 4. And no, I think it's no, 1 over 4 minus 1. Yeah, that sounds good. So if we eventually solve the exponents of v, so we would be having negative 3 over 4. And if we talk about this, so we can write this as 1 minus u to the negative 1 over 2, and that can also be written as 1 over 2 minus 1 dv, right? And yeah, everything is good. Now again, from the definition of the beta function, this integral shows beta of 1 over 4 comma 1 over 2. Believe me guys, if you're not sure about the beta function, you would find a lot of difficulties to understand this proof, or maybe this video. So here we are having k of 1 over square root of 2 equals the square root of 2 over 4 times beta of 1 over 4 times comma 1 over 2. Okay, now, wow, that is really great. Okay, so now next again we have to just evaluate this here. So it is gamma of 1 over 4 times gamma of 1 over 2 over, when you add this up, so it's 3 over 4, right? Okay, so now gamma of 3 over 4 we have computed as pi, oh, what was that? Wait a second, that was, I think, pi times the square root of 2 over gamma of 1 over 4. So gamma of 3 over 4 is pi times the square root of 2 over gamma of 1 over 4. So we can just plug that over there. So basically our k of 1 over root 2 equals the square root of 2 over 4, right? And then we are having some sort of this the square root of 2 over 4, and this gamma of 1 over 2 can be written as the square root of pi, and this is gamma of 1 over 4 over this is pi times the square root of 2 over gamma of 1 over 4. So here we got rid of these things, and and again we got rid of this one after applying the square root over there. I hope you understand that. So it comes out to be k of 1 over root 2 equals 1 over 4 times gamma squared of 1 over 4 over square root of pi. That is really crazy. And now let me just get you a goosebump right here. If we talk about the one we evaluated for the beta of 1 over 4 comma 1 over 4, so we had beta of 1 over 4 comma 1 over 4, we had evaluated it as gamma squared of 1 over 4 over square root of pi. And if we talk about the k of, oh wait a second, why I'm wrong with k? K of 1 over root 2. So it's 1 over 4 times gamma squared of 1 over 4 over square root of pi. And this thing, guess what? This is the same result for beta of 1 over 4 comma 1 over 4. So here we are having the elliptic integral evaluated at k, this small k equals 1 over square root of 2 equals beta of 1 over 4 comma 1 over 4 over 4. The relation between the elliptic integral and beta function. And basically, you know what's the motive of this video? We have to calculate the value of k of 1 over square root of 2, which we already did here. that is gamma squared of 1 over 4 times the square root of pi. So you know what, believe me guys, when we would be proving that crazy Ramanujan's pi formula, we would be using this thing, this result, this, remember this date, this video, and we would be using that for sure. So that is why I would say I'm just generating some curiosity in you, that you have to just remind me that Aman, you promised me, or maybe I'm just gonna take a lot of time to prove this down, but it's your responsibility to just comment in this video that Aman, you have to prove this down. You have to remind me that I have to prove the Ramanujan's pi formula. Wow, that's really amazing. So again guys, if you want to learn something from this video, please make sure to like, subscribe and share. And if you have any kind of doubt so far, so you are free to ask me in the comment section. I'll make sure to just reply over your doubt as fast as possible. So yeah guys, goodbye, take care, and you know what's the obstacle in between me and the Ramanujan's pi formula? Basically, it is the modular machinery. It demands modular machinery, and I'm slightly having trouble understanding that. So basically, I need time to understand that. And if even I have searched the other, if there is any other way by which we can prove that down, rather than just going through the modular machinery, but the most efficient way is through modular machinery. So we have to go through that. Basically, I have to go through that. So if once I just went through that, I would just make a video on that too, and then we would be continuing proving the Ramanujan's pi formula. Wow, I'm really excited about that. Okay, bye. Okay, guys, goodbye. Take care. Love you, and stay tuned for the next video, guys, because I'm having a lot of things for you guys. Love you, bye. Love you, guys. I'm just waiting for this video to be for 39 minutes. Whoa, it's good. Oh, I'm sorry, 37 minutes. Sorry. Goodbye, guys. Love you. Take care.